This actually works out pretty good because I thought I had too many slides and I might go over that half hour. For those of you that don't know me, I'm the System Administration Team Lead at 171. So basically we're going to go over the project structure, how we do things a little bit more, how we base the project. We've got about 10 people working on Lustre. Then I'll cover our computing platforms, go over some of our network design and our technology. Then I'll cover how we do our software release. This is a big deal. We have production users, so we want to make sure that the software is quality and really good for production. Then I'll cover the operation management. Go over some next steps and what we're planning for the future. I'll talk about Hyperion, which is a large-scale test cluster that we're implementing with a lot of vendor partners. And then I'll go over some of our concerns. Who are all these people? Mark Berry, who we have met, who's our project lead. He kind of covers all the teams. We've got a software team, a sysadmin team, and then he handles a lot of the contacts and interfacing with some other teams. As I mentioned, I'm the team lead for the administration and operations side. We basically do all of our day-to-day administration. We're the ones that assemble clusters, build it, install it, get it all running. We handle all of our software upgrades, our hardware upgrades. Our operations staff has a hardware repair team that we train to do all of our hardware repair. And that includes our DVM disks. It also includes all of our OSS and MDS systems. So if memory fails, we call these guys up and take care of it. We also have Richard Hedges, who does a lot of our user application support. He's familiar with a lot of the I/O patterns that the users use in the codes, and he'll often go out and talk to the users and help them get their I/O working better with customers. There's 4 full-time employees. About 3.5 of those are system administrators. Half of Richard's time is also in IT, and then there's the hardware repair team. For software development, Jim Redwood is the team lead for that. We've got a few other software developers. There's 4 full-time total. They're basically responsible for looking at bugs, fixing them, doing build issues, quality assurance. We develop some of our own tools in-house to help monitor us. Make sure everything's running smoothly. That's a good question. The question was how many labor hours are associated with cluster. We typically have 4 major in-production clusters, and those are assigned to everybody. So there's pretty much 4 full-time on the sysadmin side, 4 full-time on the software development side. And that's year-round. So we're a cluster. So the question is how many server and cluster nodes do you have? I'll get into some of that a little bit later, but we have roughly 200 servers and about 3,000, 3,500 clients on each of our 2 centers. You'll see a little bit more of that in So there's a couple philosophies that we've had and grown through with high-performance computing. We started out with what we call the islands of storage. We basically had a cluster, grab some storage, attach it all, and same high-speed interconnect. So let's just say infinity is some imaginary number. In the upper picture up there, you'll see that you basically have a high-speed interconnect, and up here you've got some amount of disk that's all directly attached, and a login node and some amount of compute nodes, and that's a cluster. The storage is directly attached to it. The data access is really fast. It's all on a high-speed network. Unfortunately, if you want to run your same job using your same data on another cluster, you've got to copy it over to another cluster that has its own local storage. So having lots of copies of data around is pretty inefficient, and users start to complain a lot. It's hard to manage. So we've moved on to what we call peninsulas of computation. So we'll have an actual storage network in here and a file system that's attached to it. And then we'll have a couple of separate clusters that have gateway nodes, those routers. And those will all be connected to the storage network, and that gives us a global file system. We mount the file system on all of our clusters that are tied into the storage network. So you have fewer copies of the data lying around because the users can access it anywhere. It's also redundant. If one of our file systems goes down, there's another one that's still up, and users can start writing to it. And some users will use one file system, some use the other, so our center is pretty productive all the time. One of the downsides is that there's extra network latency. The servers aren't connected to that high-speed network. They're now on a storage network, which for our purposes can be huge. A little bit more on the peninsulas. You can see we've got, this is fairly accurate for our center. We've got an L-Scratch A file system. All of our electrical file systems are Scratch file systems. We don't back the data up. The users are responsible for making their own backups. We do try to give them a higher reliability, but if the data is lost, sorry, we'll move on. Hopefully they'll pull that. So hence Scratch in the name. And so we'll have a collection of core routers that are in the middle, that are basically the core of that storage network. And then we create what we call edge routers that may be in different buildings, or they might be across the machine floor. And typically we'll connect up one or two compute clusters near one file system, so that some file systems are more local. They'll just be using the backplanes of the switches rather than actually going all the way through the core and reducing all that network. We try and encourage users that are on the same cluster as an edge router to actually use that local file system. They'll get better performance, and it won't tie up the core. But if they do need data off the other file system, it's still available on that. This is our open computing facility. We have two computing facilities. One's the open side, and the other one's the secure side. By an air gap, so if you want to move data from one to the other, it's all secret. Generally, you only move it in one direction. So this is kind of what our open facility looks like down here. For those in the back, you may not be able to see it. We have a total of about 100 teraflops of computing power and close to 2 petabytes of actual storage. IGS, which is up here, is one of our test clusters, and that, along with ALC, is where we do a lot of our medium scale testing. So that's kind of a development resource. I laid it out this way because they're actually in different buildings. We've got one file system over in one building, another file system in another, and we just have edge routers located in each building that these different clusters to the file system. But, like I said, everything's mounted everywhere. We've moved to a philosophy of having 2 file systems. As I mentioned earlier, that was for redundancy purposes. That way, if we want to upgrade one file system, we can take it down, do all the upgrades, the users can still operate, and then a day or two later, we can upgrade the other file system. So this is the same map, but this is how LLNL is doing. We have one big flat TCP0 network. There's a lot of just TCP routes that are routed from one subnet to the other. Typically, on each edge switch, we'll have a set of subnets. So it makes our routing pretty simple. But then you'll see other clusters, like, there's 2 along networks on here because we wanted to divide it up into half so that the production half of ALC has one set of dedicated routers and the developers half of ALC has its own dedicated set of routers. So physically it's one along network, but we provided a lot of efficiency. We've got a couple of InfiniBand over here, there's an along 4 cluster. A little bit of everything. Our secure computing facility is a little bit different. It's all in one building. Like you'll see VGL up there at close to 600 teraflops. It's a big beast, and it can overrun any of these file systems pretty easily. And we've seen users do that a lot. In fact, Richard's talk later will be about what some of the users have done. We've got a total of about 665 teraflops. 3.5 petabytes of this. And again, it's all broken up with edge switches. can see here. Each little blue box is its own edge switch, and I'll kind of give you the network bandwidth for each one of those edge switches. So BlueJean has about 75 gigabytes worth of network bandwidth available for you. You'll notice the file systems don't have anywhere near that much. So BlueJean is pretty much small. This is an example of how we define edge switches. So we'll have a couple edge switches in each of the clusters will be connected to the file system. So because these are all kind of on the back plane, access to this file system from these clusters will get a little bit of performance. Anybody else coming through is limited to this 30 gigabit per second flow. So any of these other clusters would be flawed from that section of the network. No, that's LNet. LNet's view. So this is one InfiniBand cluster, and it has its own set of gateways. And LNet handles all of the TCP to InfiniBand. So this is one of our next steps with LNet. Our clusters are growing too big, and our file systems are expanding, and so 2 little edge routers are not going to be sufficient enough to actually contain all the network connections that we have. So we're going to be adding additional edge switches that are all attached to the same file system, and we're moving from these down here, which were dual DB, we're moving to a single 10 DB. And so we don't want traffic from some of these routers to go through one of these edge switches into the core and back down here to get to the new servers, where the gateway node can go directly through the switch back. So we're going to be adding some additional TCP networks, which complicates our LNet networks, but it's complicated the inlet. We've actually done most of this. All the connections are in place, but right now we're actually routing through the core because we have to modify a lot of clients to have their knowledge of these TCP networks. And that's right here. So the benefits are we reduce the network traffic through the core switches, just using the backplanes of those edge switches will reduce the latency, keeps the traffic local. It'll save us a lot of money in terms of the amount of networking infrastructure we would need in the core to handle all the additional traffic. One of the issues we have, though, is that we need dynamic pins. Right now, you can easily add a route on a routing cluster. So if you want to bridge from InfiniBand to some new network, you can dynamically add the routes to a router. But that doesn't work for the TCP clients. They need to have knowledge of the TCP1 and TCP2 network. So we really need to be able to add a native dynamic routing system, but we can't do that. You have to unload the ONN modules, reload them, hook up the new module.com. Unfortunately, when you have more than one file system on the node, you have to unmount all those file systems to get the modules on the node. So that basically takes the whole node down. So I think we're going to open it up on that and see if we can get that. This is another thing that we do that is kind of interesting. I don't know if any of this is good, but we basically created a new cluster where we can provide a fast pipe for our archival storage. We call it Slate. And it basically has a bunch of fat pipes into the Lustre network, and then a bunch of pipes into the storage network. And it's not the cluster's not busy running compute jobs. It's just running data transfer jobs. So people can log on there and do their FTPs storage. And it's not impacting production. Typically, users on the compute clusters would, at the end of their job, they would start up some batch FTP script and be wasting their compute cycles trying to transfer data to storage. So this makes things a little more. Software release is a big deal. We go through a lot of steps before we can actually do that. Just now So we do a lot of sanity tests in our build farm. That just runs through a lot of the Lustre sanity tests. Then we'll do some small scale testing and testing that has maybe 8, 16 nodes. Then we'll move on to some mid scale testing. And we do that on the other development cluster for BlueGL. And we're going to be ensuring the 64 node cluster. Then we move on to large scale testing on the ANC, which is about 400 clients. And then occasionally we'll do giant scale testing on about 1,100 nodes. And these are what we call dedicated system times. We don't use this just for Lustre testing. We actually try and test our entire release. We've packaged Lustre as part of our OS upgrades. So it used to be that if we had some Lustre bug fixes, we just put it out there and we're trying to get a lot more mature with our own software release as well. So Lustre is now yet another component of our operating system. So we'll usually bundle up a whole bunch of buckets, so whether it's MPI, hybrid, or Lustre is just another component that gets put into the release. So we'll do a dedicated system time where we take one of our large compute clusters and take it for a whole day, and we just run through a whole bunch of tests using every aspect of the operating system to make sure that it's a production release. And then there's a wide variety of things that we run that are constant specific. So I'm sure you guys all know IOR optimization, etc. Another interesting thing we're doing is that the developers are using Lustre for their home file system. So they know what it is that they want to leave their own document. If they're going to say it's good enough for other users, it's got to be good enough for them too. So they've got a small so that uncovers some of the bugs that we don't have along in this way much wildlife. And we typically carry about 150 patches from the base release to actually make these work on our system. And carrying that many patches, testing them all, right now we're midway through our migration from 1.6. It's going a lot smoother than I thought it would be. The steps are pretty simple. One of the things that we noticed is that 1.6 doesn't have an X-Script, which we relied pretty heavily on in 1.4, so we ended up writing one. And we decided to roll on the servers before the clients. That eliminated a whole set of testing we would have to do with some of the clients before the server. So all of our servers are now running a 1.6.2 variant, where we've got about 160 patches above the base 1.6.2. And we're basically only doing our x86 64 clients. And all of our legacy 1, 86, 90, 64, we're going to be retiring those soon, and so that we're going to use the rest of our support. They're actually running an older version of our base software. But again, you can see that the 1.4.8 release we're running prior to this, we're still carrying about 150. There's a lot of software development that goes on. The 1.4 clients can mount a 1.6 file system because they were originally created for 1.4 and migrated to 1.6. If we were to field a new formatting of 1.6 without we could create it at 1.4 migrated. Or the second bullet here, actually we have developed a tool that will read the 1.6 client logs and convert them to a 1.4 file. It works and actually listed that we have to discuss in this. It's just a patch to help them. The other option we did not know. On the operations management side, we usually go for the concept that we call savings. If everything is the same, it's easier to manage. The more variety you have in configurations that are related. So we moved to a storage scalable unit, which we borrowed from the compute clusters. And it's basically just building blocks that we can build or expand the files with. So the picture over here is there's basically 4 racks of disks, and the center rack is all infrastructure. that has our OSS in it. So it's a nice little 5-rack unit that you can just plop on the floor anytime you want to. So we recently have been expanding one of our file systems. It started out at about 800 terabytes. By the middle of next week, it should be 10. So that makes things really easy. It also makes it easy on the hardware repair team because we train them to work on this hardware, and the more varieties we have, the more notice about it. It makes it difficult for them to get everything straight. You don't want someone putting the wrong type of memory in the code. It just doesn't work. For our operators, we've developed some training courses locally to help them figure out how to debug Lustre, how to scroll through the console logs and the Lustre logs, DBA logs, and that way they can do some amount of problem determination before they actually end up having the page assistant turn off. We have a local wiki that we put a lot of our procedures. If we encounter new bugs or problems with the release, we usually put those up on the wiki so that the other sysadmins can have a quick reference of whatever they're seeing a new bug. And then we've written a number of scripts in problem determination. How to track down the one user that's writing 4 bytes at a time rather than 1 byte. How do we track down a user that's dumping 100,000 files in an hour? So we've done a lot of scripts like that. And LNT, which I think you guys have heard about, it was presented at one of the last groups. It's up on self storage, the URL is up there. We basically took an old Python program and we converted it to the client Java. There's a MySQL database backend that stores historical data. So it's got basically your read and write rates, your CPU percentages. So it's a nice performance tracking tool. You can generate your graphs. We've actually been using that lately to characterize the file systems to see what our bandwidth is doing. One thing it does though, it aggregates time down to an hour for some of the statistics. Other statistics are raw, which is every 5 seconds. So, yeah. Yes, so the question was, do we run 24 hours? Yes. The other question was, do we use it to keep track of when the system is down? In fact, one of these lines that the OSS isn't able to be contacted should go away. So you could actually use this to see if anything's wrong. No, I don't think we've actually generated that, but rather it's all data. So we store every 5 seconds, every OST. We also store OSS aggregate information. So if you're just looking at the particular node, we have that too. And then on the far right, which is really hard to see, this is a router proof. So if you have gateway nodes in each of your clusters, we track the router information as well. And this big table on the side here is ABS statistics. So feel free to download it off of and send us an email. Some of our next steps, we've got a couple large procurements that are coming in. Dawn will be a half file system, and we're looking at building a file system with it that's 96 gigabytes a second, about 4 petabytes inside. And that's for the end of this year. Sequoia, which is in the 2011 timeframe, is 10 petabytes, 512 gigabytes a second, and 50 petabytes a second. So that's going to be big. Lots of hard work. It's hard to say. I mean, we're exploring new technologies. We're looking at rather than the FAQD core network, we're looking at Coding core network, optical QDR range. That's what we're working for. We've got 3 years to do it, so it's going to be a problem. Related to that, if Sequoia comes in with an InfiniBand network, how are we going to connect it to our legacy FAQD? So we might be implementing a router cluster where we just have a cluster of nothing but gateway nodes that bridges InfiniBand to FAQD or 4BD. also evaluating ZFS, both user space and internal. We've done a lot of work at kind of comparing the two to see which one works better. But if we have the time to talk to them about it, we'll land over a couple days to do most of the work. And then failover, we've been pretty paranoid about failover. We have failover capability enabled on the file systems, but we don't have failover there, so the process is the same. We've been pretty paranoid about data too. We want to make sure that we fail over that device is consistent. So we're working on a manual failover setup right now. We had encountered some rate controller issues that were causing some cache on. So we're trying to test out that. And the Ethereum is a really big deal. We've got an AL, so we're finding a big hammer to it's going to replace ALC as a large-scale Lustre test cluster. And it's a partnership with the vendor community, including Sun. I think some of our partners are Cisco and Dell. We're going to get a big giant, about 152 nodes, and we're going to use it to test out a lot of the emerging technologies. This is how we're going to split this stuff like this. So we're going to be testing out OPED and PDR and 40, 100 and whatever comes out. And we're basically going to be, it's going to be a technology refresh. So we're going to use the scalability concept, and as time moves on, as the nodes get bigger and better, as the technology gets better, we'll be swapping out some of the older stuff, and older stuff, and just keep it with it. And this Sun as a partner, they can log in, and they're going to have time on this machine to do full-scale testing, which should really help out eliminate some of the need that they might need on other customers to go out and use that. I don't know what to stress on that. It's basically the answer to that. I'm not sure if that's something. For the file system, there's actually going to be 3 file systems with 3 different disciplines. We've got an LSI, UDN, and Sun or something else. So the total would be about 1.6 petabytes. And we have 2 networks that we can evaluate. We have an NVD infrastructure and actually internet networks. So we can kind of find the best breed and see which one is best guess for that scale. Pretty much. Yeah. See which one's better. What's the better architecture going forward? InfiniBand right now is order of magnitude cheaper than some of the NVD hardware. But if they get 40 or 100 AD, then it's really price competitive. We want to test out both. Also, our current infrastructure with the solid code is all NVD. So we want to see how it compares, and we can use this as a test bed to see how it would work to migrate from the NVD to some of our concerns, obviously space management is a big one. How do you manage a 50 petabyte file system? What it is? How long is your footage purchase? Right? Our users kind of just dump data and leave it out there, and we're left to clean up the mess. So if the file system gets to be 80% full, we want to go away all the files that haven't been accessed in the last 20 days. How do we do it? We've got some scripts in place now, but generally, if you're wanting to look at the 8 time, you've got to look at some other file system. Or do you have to use this version? We had talked about actually making a kernel thread on the NBS system in the background, which is kind of scanning all the time. So that's a big deal. A lot of the tools don't scale, right? There's a lot of RC probably machines. RC for 50 petabyte file systems. So some of the things that and then also moving data to the archive efficiency. And I think that the higher sort of but it's something that's then scale it. Adaptive timeouts that they mentioned, we've been working heavily over the past month to get that better. And then there's the issue of multi-unit cluster organization. As these clusters get bigger and the nodes have more cores, will be better. And then the way the log node, as you can see, is seamless failover. We want to failover to just work out the box. No, the question was, is that a concern based on the fact that we are not confident? No, I think a lot of it's historical. We've had some control issues, but we also have to know that it always seems to fall patterns. It would be nice if someone said, here's the package, failover. Install the software, here's the rules, just let it go. Yeah. It's a little complicated issue. There's so many different possibilities to go over how you package issues. How you make this original. It's a complicated problem. That's something we're going to explore in the area. We haven't done much of it ourselves. Kind of really have a need for it. I think with Hyperion, we're going to get a lot of experience with that because there's a lot of different vendor partners that are going to want to test different things. And the easiest way to do that is to set up virtualization on all these nodes, and then they can load whatever OS they want on